2012 NZQA scholarship paper, physics. There we go. Okay, when I'm faced with an exam paper, the very first thing I will do is to actually have a quick read over all of it, particularly the first page, just to check that this paper is what I'm expecting it to be. So indeed it says, Scholarship 2012 Physics, I'm not studying the English one, or Performing Arts, or whatever. 2 PM Wednesday, 21st November 2012. Time allowed 3 hours. Total marks 48. Then we've got a list of instructions. Check that your number on your admission slip is the same as the number on the top of this page. It's worth doing that. Otherwise, your exam paper could get very lost. That will cause you stress. Key instructions: you should answer all the questions in this booklet. That's worth remembering. Every question carries weight. I should tackle all the questions. For all describe or explain questions, the answers should be written or drawn clearly, with all logic fully explained. I mean, in one sense that's obvious, but they're making the point presumably because people don't do that sometimes. And actually I'm reminded here of a long time ago when I was at university, I saw a English literature exam paper, and on the front of it said all students are reminded that answers should be relevant to the questions. And I thought, what? Surely answers are always relevant to the questions, but no, apparently what happens is that students come in with their pre-prepared essays, and they say, oh, this is a question on Pride and Prejudice, I'm going to write my pre-prepared Pride and Prejudice essay, and not actually read what the question says. So we will be reading our questions. For all numerical answers, full working must be shown, and the answer must be rounded to the correct number of significant figures. So let's just check to do that, and given with the correct SI unit. Formulae you may find useful are given on page 2. Let's just turn that over and see that, yes indeed, there's you probably can't see that on the screen, but there's a whole long list of formulae there on page 2. If you need more room for any answer, use extra space at the back of the booklet. And yep, I've got extra space there. Check that this booklet has pages 2 to 22 in the correct order and none of these is blank. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, ouch, these are looking hard, 14, 15, 16, 17, 18, 19, 20, 21, 22. You're advised to spend approximately 30 minutes on each question. Presumably then there are 6 questions, which is what I'm expecting because that's what the pattern has been. Yeah, 6 questions, so they're going to each carry equal credit. Remember to hand the booklet back to the supervisor at the end. That makes perfect sense. Okay, so now I'm happy with the instructions. They are what I was expecting them to be. I'm going to go over, and I'm going to briefly look at all the questions here. I'm not going to start doing any just at the moment. And the reason why is that I want to do the questions in the order that best suits me. And of course the order that best suits me may not be the same order as best suits you. 2 reasons for doing this. The first one is that I just want to do my best questions first. That's going to give me confidence that, hey, this exam is not so hard. There are bits in there that I can do really well. So it's given me confidence, and if I got confidence on the early bits, that'll hopefully carry over to the later bits, which I might find harder. Secondly, I don't want to waste time struggling on a question that I'm not going to get out, and then find that there are a couple of questions which I could have done, but I just run out of time, and I can't get the credit on it because I've wasted time somewhere else. So I want to get the credit that I know I can get as quickly as possible, so that gives me more time to do the harder things. Okay, so let's have a look at the questions. Question 1, modern physics. Now, when you look at these scholarship papers, the questions always have titles. Sometimes the title is actually quite helpful. It starts you thinking along the right lines. So, modern physics, really that means anything from 1900 onwards, but I'm expecting to see things about wave-particle duality, diffraction of particles, that kind of thing in there. So let's have a look through. Charge on the electron, speed of light is given. In an experiment to investigate the photoelectric effect, light of wavelength lambda is incident on a metal surface and the current is produced. The current is reduced by applying potential difference V between the metal surface and the collecting plate. Yep, that's the standard photoelectric experiment. When the current is reduced to zero, derive an equation relating the wavelength, voltage, and the work function of the metal, and provide a full explanation of the derivation. Next part, a classical wave explanation fails to explain the experimental results of the photoelectric effect. Discuss this statement. This is really what Einstein was talking about. Then on to part B, nuclear mass of that much, which is stationary with respect to an observer, undergoes fission. The nucleus breaks into 2 equal parts. There's some kinetic energy, 2 parts brought to rest. Calculate a total decrease in the mass, and therefore the individual rest mass. The masses, so we're talking a fission example, mass converted to energy equals mc squared. According to Einstein's special theory of relativity, the mass of an object with a velocity v relative to an observer is given by that complicated formula there. Discuss the physical significance of this relationship. So there's a discuss question. What does that mean? Where does that relationship go? By considering the effects of special relativity, calculate the speed of the 2 masses in part 1 above before they're brought to rest. Now, you don't do special relativity at school, but I think that's something that we can bring in, and it's a challenging question to bring that new information in, but to apply it to something that you are familiar with, nuclear fission. Okay, so that's a waves E equals mc squared sort of question. I think I'm reasonably happy on that. But let's look at question 2. Inductance. 75 watt electric light bulb is designed to run on a 50 hertz supply. Actually, I'll just write on the board here. So question 1 is photoelectric effect and fission equals mc squared, that sort of thing. Question 2, inductance. That tells us exactly what we're going on. 75 watt electric light bulb, 0 inductance, is designed to run from 50 hertz AC supply of that voltage. If the only available supply is 240 volts RMS and 50 hertz, the bulb can be operated at the correct power by placing in series with it either a resistance R or an inductance L. So here we're talking about not putting the right amount of current at the right voltage through that bulb. Find the values of R and L and the power drawn from the supply in each case. So we've got a AC circuit question there. Part B, when an alternating voltage is applied across a coil wrapped around an iron core, an aluminium ring around the core will float at some height above the coil. That's a nice demo if you've not seen that before. Explain why this happens. Aluminium ring on an iron core, so we're talking about induced currents, creating fields, Lenz's law, that kind of thing. So question 2, I'm just going to note down. So we're about AC circuits. We're on sort of Lenz's law and induction. Explain, possibly with the aid of a diagram, how such a coil would be wound so this effect would not take place. I have to think about that one. Diagrams are always good. well, you could wind a coil somewhere else, I guess. But we'll see how we go on that one. To reduce the heating of the iron core, thin sheets of iron are glued together. The glue that holds the thin sheets together must have specific electrical properties. Suggest at least one electrical property of the glue. State why is this important. So this again, we're talking induction here. What's going to happen? Of course, if you've got induction, you've got currents going everywhere. Currents heat things up. I think that's along the lines of that one. So current and heating. Right, question 3. Doppler effect. Speed of sound in air is 340 meters per second. Acceleration due to gravity 9.81 meters per second square. They're giving you that. Actually, I think it's well worth knowing those things. When the Doppler effect occurs, it is known that the apparent frequency of the sound is increased as the source of the sound moves towards the stationary observer. Explain why the frequency increase occurs. So a straightforward question. But get that physics right, explain why that occurs, and I think a diagram there would go down very well. So question 3, Doppler. Part B, explain qualitatively. Qualitatively means not using numbers, don't do calculations. Explain qualitatively what would happen to the apparent frequency if the observer moved at constant velocity towards the moving source. So now not only the source is moving, but the observer is moving as well. Ben is on the top floor of an apartment building and has a phone that emits a single ringing tone of 440 Hertz. Unfortunately, while picking up the ringing phone, Ben drops it. Yeah, I can see where this one's going. Ben drops it so that it falls off the edge of the 0.7 meters high top floor ledge he is leaning on. Sometime later, Ben hears a reduced frequency of 416.2 Hertz. He's got a good ear to pick it to that precision. The height of each floor is 3.10 meters. This is one of those scholarship questions which they must love dreaming up. Calculate the number of floors that the phone must have fallen when it emits the wave that Ben hears is 416.2 Hertz. Sounds complicated. I don't think it is. It's just Doppler effect. We know what the frequency was. We know what it is. Therefore, we can work out how fast it's going, and because it's in free fall, if we know how fast it's going, we know how far it must have fallen under gravity to get to that velocity. I think that'll be fun to do. Frankie is watching Ben from the top of an identical apartment building on the other side of the street. Frankie is at the same height, but is 40 meters away from Ben. For the wave that Ben hears is 416.2 Hertz, calculate the frequency that Frankie would hear. I have to think about that one a bit more. Okay, Doppler effect. Well, probably drawing a diagram might be a good idea there to see what we've got. So question 3 really is Doppler effect and a bit of linear acceleration under gravity. Question 4, motion. Not sure that's desperately helpful, but let's see. Ball X is released from a height h and hits the ground with speed v. At precisely the same time ball X is dropped, or at precisely the same time ball X is dropped, ball Y is launched straight up from the ground at a v. Show that the balls will pass each other at a point ℏ from the release point of ball X. So again, this is motion, gravitational field, so constant acceleration. So you've got all your kinematics formulae, and somehow they'll come out to show that the balls pass each other a quarter of the way up. Use physical principles to explain this result. So physical principles, talking about things like momentum, energy. Yep, we'll see how that one goes. A ball of mass m makes a head-on elastic collision with a stationary secondary ball of mass big M and rebounds with a speed equal to 1/3 of its original speed. Show that the mass of the second ball is equal to 2m. So we're talking collisions, so momentum is conserved, and I see the magic words elastic collision in there, so that we know kinetic energy is conserved. So there are your equations, and show that the solution is that big M equals 2M. So we're talking kinetic energy, momentum, again linear acceleration under gravity. Part D, a pair of balls, both of mass small m, are sliding along a horizontal frictionless groove towards a stationary third ball, also of mass m, as shown in the following diagram. For the collision of a pair of objects, the coefficient of restitution is calculated by sigma equals the difference in the velocities after the collision divided by the differences in the velocities before the collision. So it's a measure of what happens on the collision. The coefficient of restitution of these balls is 0.4. Show that there are just 3 collisions between the balls, and the sum of the final velocities of the 3 balls is 8 meters per second. That looks a little bit involved. I mean, obviously ball B is going to hit ball C. Ball C is going to go off. Ball B might rebound back and hit ball A, which goes off to the left or something like that. I think this is all about working out what's going to happen with those collisions. Looks a little nasty, that one. But again, momentum transfer, kinetic energy, that kind of thing. Question 5, physics compilation. That looks threatening. That sounds like we're going to throw in everything you've ever done in level 1, 2 and 3 all in the same question, which of course they're allowed to do at scholarship. The acceleration due to gravity on the surface of Mars is 3.71 meters per second squared. Mars has a radius of 3,395 kilometers, and its period of revolution is 24.62 hours. Show that the satellite needs to be positioned 2.04 times 10 to the 7 meters from the centre of Mars so that it remains stationary with respect to an observer on that planet. So geostationary orbit on Mars, what's the distance, what's the radius have to be? So this is a circular motion for the orbit, Newton's law of gravitation for the centripetal force, balance them out, hopefully we'll get the right answer out. So question 5, we're talking about centripetal force, gravity, part B. 12 identical 1-volt batteries are connected in an electrical circuit as shown in the figure above. And they are all in a nice ring. They've not drawn the circuit diagram of it. They've actually physically drawn the batteries, but it looks like the little knob on them, the positive end is pointing the same way for each of them. What will be the reading on the voltmeter? Explain your answer. What a fun question that is. Kirchhoff's laws. Assume each battery has the same internal resistance and the voltmeter has infinite resistance. One hopes they've got an internal resistance, otherwise there's going to be some massive current flowing around there. The current below consists of, or the circuit below consists of 8 resistors, each with resistance R. Explain why B and D are the same potential. So again, this looks like Kirchhoff's laws. Calculate the effective resistance between A and C. Again, you can see the diagram there, so it looks like a bit of logical thinking. Usually for networks like that, just applying your formula for resistors in series, resistors in parallel isn't sufficient to tackle that. We need a bit more natural thinking, and symmetry is a very good way of going. they're identical resistors, that's going to help a lot, I think. Calculate the effective resistance between A and C. Again, we'll come to that, have a good think about that one. Part D, so again, sort of Kirchhoff's laws in DC. Part D, the force between a pair of charges is given by Coulomb's law. There we go, inverse square law. A charge Q and another charge 4Q are placed at the coordinates x equals 0 and x equals L. Find where on the line between them the resultant electrostatic force of a third charge is 0. So two charges, one there, where do we place another one, so the force on it is 0. Seems reasonable enough. So Coulomb's law forces. Question 6, simple harmonic gravity. Okay, right, so straight away I'm thinking from that title, simple harmonic motion, and I'm thinking gravitational fields. And we're given a whole lot of information of the Earth. Imagine that a hole is drilled from the South Pole through the centre of the Earth to the North Pole. By using Newton's law of gravitation, show that if Earth has uniform internal density ρ, ignoring air resistance, an object dropped into the hole will perform simple harmonic motion. And then a hint, worth reading the hints. For an object at distance r from the centre of the Earth, the net gravitational force on the object, due to those parts of the Earth's mass that lie at distances greater than r, is 0. So it's giving you a bit of a hint how to do that, and we'll kind of come on to this question, but it's saying that if you're at this radius r, then all this mass out here actually contributes nothing to the overall force. The sort of mass here balances the mass out here, so you only need to consider that bit in there. Simple harmonic motion, so all we need to do is to prove it's simple harmonic motion is to show that the force is proportional to minus the displacement. Calculate the period of this simple harmonic motion. That's just finding that constant relating force to displacement or acceleration to displacement. Explain in what way this period is related to the orbital period of satellites in low Earth orbits. Looks like it's going back to our question about orbiting Mars. Discuss the differences in the motion of the falling object that will be observed if the hole were drilled from an equatorial position rather than from the South Pole. So across the equator, the obvious difference is that the Earth is rotating, so we've got an effect due to rotation as well. We'll have to have a good think what that will do when we get there. So those are 6 questions. I'll check over question 7 buried there. Okay, Coulomb's law. So question 6 is about simple harmonic motion, again about gravity. Okay, so I'm getting off camera there. So having looked at that, I'd like to do the questions I'm most confident with first. I think having seen them, I'm quite tempted to tackle question 6 first of all. Then probably the photoelectric one, the nuclear physics there. So let's do that first of all. Let's do that second. Physics compilations scare me a bit, but I'm going to go at question 5 next. And then I quite like the look at the Doppler question. I didn't think that was too bad, so let's do question 4, and we'll look at the sort of the last 2 out when we come to them. So that's how I'm going to go and tackle this paper. I've taken a bit longer to explain through it than I would if I were actually doing it myself, but I'm now reasonably confident what to expect, and hopefully have a good go at doing that.